Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our distinguished speaker, Professor Deborah Shah from MIT. Professor Shah is a professor in the Department of EECS at MIT. He is the founding director of the Statistics and Data Science Center at MIT. He is a member of the Institute for Data Systems and Society, a laboratory for information and decision systems, CS and AI laboratory, and operations research center at MIT. He has made fundamental contributions in the theory of large complex networks, which includes network algorithms, stochastic networks, network information theory, and large-scale statistical inference. His current research interests include algorithms for machine learning, causal inference, and social data processing. He has received the best awards from Inform's Applied Probability Society, NeurIPS, ACM Sigmatrix, and IEEE Infocom. He has received the Erlang Prize for Inform's Applied Probability Society and Rising Star Award from ACM Sigmatrix. He is a distinguished young alumni of his alma mater, IIT Bombay. In 2013, he founded the machine learning startup Select, which helps retailers with optimizing inventory by accurate demand forecasting. In August 2019, Select was acquired by Nike. Today, Professor Shah is going to talk about synthetic interventions. Please join me in welcoming him.
Well, thank you, Zoran, and thank you, organizers, for inviting me to this online seminar series. Thank you, everyone, for being there remotely, spending a valuable hour of your time with me here. Today, I would like to talk about a method called synthetic interventions. This method is primarily a method for doing causal inference or estimating counterfactuals using observational data. This is part of the thesis of Anish Agarwal and Dennis Shen, who are both graduate students at MIT. It's also done in collaboration with Abdullah Alomar and Romain Cosson, who are now graduate students at MIT as well. So as I go through the talk, what I would like to do is first just to explain where such a method for causal inference using observational study become relevant. In a sense, this talk/seminar series has been made feasible because of, as we know, COVID-19. And COVID-19 has provided a good opportunity to explain this method. So let's look at this chart. What I'm plotting here is a number of deaths in United States. On x-axis, I'm plotting days, where 0 indicates the 80th, day on which 80th death was reported. Okay, and of course, as you can see, after that 80th death report, this is talking about first 2 weeks of trajectory of number of deaths. Again, this is an early part. As we know now, we are getting closer to 200,000 deaths, but this is an early part, and let's focus a little bit at that. And in particular, let's imagine that you and I are policymakers, and we are trying to decide what is the right policy to implement in United States on day 0 to achieve a variety of different types of health outcomes, potentially balanced with other factors such as economic impact and so on. As we look at United States, it's worth looking at what happened in those first 2 weeks across the globe. In particular, if we look at Google mobility data, this is a brief summary of that Google mobility data. What I'm showing here is roughly 27 countries plotted on x-axis. On y-axis, there is average reduction in mobility compared to pre-COVID time. So for example, if we look at a country like Ecuador, the average mobility reduction was 60% compared to before COVID time, compared with after COVID time. Okay, so if we look at this and we have color-coded, roughly there are 3 clusters emerging. There's the countries which have low mobility reduction, US included, at least in first 2 weeks, less than 5%. There's the countries which had intermediate or moderate mobility reduction, 5 to 35, and then the country which had severe. And each of these were induced because of different types of policies. But at the end of the day, this is something that we are measuring as a proxy of policy impact on a country. Okay. And the question that one would like to ask is, what would have been the health outcome for the United States if any of these 3 different mobility restrictions were induced, of course, through different policies? In reality, of course, as we saw, it's less than 5%, but what would have happened if it was 5 to 35% or severe mobility reduction? Okay, and this is exactly the type of question that we want to answer while sitting on day 0, that is the day on which 80th death has happened, and we want to understand what would happen. Can we sort of do this counterfactuals? Okay, and as I will explain in the remainder of the talk, using the method of synthetic intervention and all the data that's available out there, what we'll be able to do by sitting at day 0, which is where the dashed line is here, we can forecast or predict 3 different outcomes: the dashed blue line, the dashed green line, and the dashed orange line, which are corresponding to, so blue corresponds to low mobility reduction, orange corresponds to moderate, and the green corresponds to severe mobility reduction in terms of number of deaths. And I'm superimposing that with dark blue line, which is the true. And in a sense, this at least visually cross-validates that, yeah, the method might have some merit. Okay. Now, this is for United States. We can say what happens to other countries. Here's what happens to United Kingdom. As we know, United Kingdom actually, like United States, did not have a strong response and hence saw a massive rise. And these were the 3 different outcomes that they would have experienced initially if they had gone through different policies. Here are 2 countries, Brazil and Turkey. At least initially, the response of Brazil and response of Turkey was of the nature where there were moderate mobility restriction, and that led to moderate rise in the death count. Similarly, in India and Ireland, India went under severe lockdown, and it was extremely slow growth initially, and similarly what Ireland experienced. Okay. So in short, if you are at day 0 and back to United States, maybe one takeaway would be that instead of severe lockdown or low mobility restriction or nothing, maybe moderate mobility restriction with careful restriction at the right places, such as retail places and transit places, could lead to flattening the curve. Anyway, so this was what a method like synthetic intervention can do. So in the rest of the talk now, I want to explain how we came about these numbers and what that method is. So the rest of the talk is going to be about how. Again, as I was told by seminar organizers, if you have questions, you can use Q&A to ask questions there. And near the end of the talk, we'll have time to go through them one by one. So synthetic intervention, that is causal inference using observation data. So let's ask the question, what is causal inference and what is the problem of it? Okay. So as we discussed in this specific scenario, we want to know the outcome, health outcome for United States under all possible scenarios, that is 3 different scenarios, even though we observe true outcome only under one scenario. And that, in a sense, in a nutshell, is the fundamental question of causal inference. Okay. How do we start thinking formally about this thing? Well, a traditional way, and in a sense, the way to think about causal inference is through framework of what's called potential outcomes framework. Effectively, what it says is that every unit, every country, every individual has multiple different latent cells, and depending on different interventions, one shows each of these different latent states corresponding to those interventions. For example, in our scenario, there might be 3 different latent states of United States. One that would be expressed under low mobility, one that will be expressed under moderate mobility restriction, or one that will be expressed under very high mobility restriction. Let's call Y as observed outcome, and in a typical setting, we would think of Y as a sequence of observations measured over times for the metric or quantity of interest. Let's say M sub D is the potential outcome that is of interest but not observed under intervention D. In our case, there are 3 different interventions: low, moderate, high. And MD over time can represent, and as we'll see in a second, represent a matrix of observations with rows corresponding to countries and columns corresponding to time. D star is a specific intervention in context of United States low restriction that we observe, or rather it's applied. And that means that sort of the observed outcome would be effectively a random variable Y, maybe in some distribution, has a relation in expectation, let's say, to the true potential outcome of interest. And of course, the goal is to estimate M sub D for all D not equals to D star. Because D equals to D star, we're observing through expectation, then maybe we want to denoise it as well. Okay, so this in a nutshell is a framework of potential outcomes. Again, I'm not going into too many details, but this is roughly what it corresponds to. There is a notion of individual treatment effect and average treatment effect. In this context, we're going to talk about average treatment effect because we are trying to understand the effect on entire United States, which is of the population of people of the United States. Okay. Now, for the purpose of this talk and to explain the method and the way, at least the genesis of this method, we would like to view this framework of potential outcomes as through a lens of tensor, a tensor which is a familiar language for, at least from the lens of machine learning. Okay. Where what we'll do is that we'll encode potential outcomes through tensors. In particular, here is a 3-ordered tensor that I'm representing. There's a notion of units, let's say countries. These are the countries in our case. Different slices here are representing different types of policies, say low mobility restriction, medium, and high. And then columns here are representing measurements over days. Okay. For example, this point may represent the number of deaths observed in United States on day T. If we go laterally, then it would represent number of deaths observed in United States at the same same day T, but under different policy, and so on. Okay, and this, in a sense, is what we observe. And of course, we don't observe the true underlying potential outcome tensor M, but a noisy version of it. Now, primary approach to estimate these potential outcomes have been roughly 2. One is what we would call experimental studies, another what I would call observational studies. In experimental studies, what you would do is you would design an appropriate experiment that can gather information about all potential outcomes, and then use that and summarize that to make eventual decision. You have to make sure that these designs are done carefully, but that's roughly what a good randomized controlled trial does. That's what has been used, for example, in clinical trials to approve or disapprove therapies, as we are going through for many vaccines right now, or in e-commerce, what's known as A/B testing. Okay. Observational studies is exactly the type of example that we are trying to understand in our running example of health outcomes for United States. Because if we wanted to do experimental studies for that case, what we would have to do is we would need 3 copies of United States. Copy 1 that has low mobility restriction, copy 2 which has moderate, and copy 3 it has high mobility restriction. Simultaneously, at the same time, we see 3 United States evolving, and then we can eventually compare. Now, it is as ridiculous as it sounds, because of course we have only one United States, and this is exactly the challenge of doing causal inference with observational studies. There are many terrific approaches out there for close to half century, if not more. And one of the prominent method in this context is synthetic control, which in a sense is what led us to think about synthetic intervention. So as I will go through remainder of the talk, I'll briefly introduce synthetic control as well as we go. All right, so let's go back to again a tensor representation. One way to view experimental study or randomized control is, let's say you have a population of patients, all the patients randomly divided into 3 groups. Group 1 gets drug type 1, group 2 gets drug type 2, and group 3 gets drug type 3. We collect measurements over time for patients, and then at the end we decide that for average over all patients, it seems that drug 1 is the best. Okay, so in a sense, in this tensor, we explored everything that's out there, then we measured it, and then we made a decision. Okay, and that's randomized control. On the other hand, you might say, well, you know what, I don't want to just have one drug for all the patients, because I know that there are young patients, there are old patients, there are patient of type A, there are patient of type B. So maybe I want patient of type A to have one type of drug and patient of type B to have another type of drug. And I don't want to do all of these experiments, but maybe what I want to do is that patient of type green might have drug A, patient of type blue might have drug B, and patient of type another might have drug C. And just based on these sparser observation, can I still make a decision that what is the best, can I make a decision that group G has drug B is the best situation, or what will be the observation outcome then? So this, in a sense, from classical randomized control, we are slowly going towards randomized control meets experimental observational studies, and we'll come back to this. But once we start viewing this in the context of tensor, this already starts giving us a flexibility of view. Back to our example, what we have is, let's say, there's a day 0 corresponding to 80th death for every country, before which all the countries had not any mobility restriction. They were as is. And so we observe what was happening to those countries or health outcomes of those countries under that no intervention policy. After that, some countries decided to do nothing. Some countries decided to impose some type of restriction. Some countries decided to do even more mobility restriction. So these are different policies, and for some countries we observed health outcome here, some countries we observed health outcome here. And ideally, we want to know all of these outcomes. Okay, and then maybe then decide that this is the best thing to do for these countries, and this is the best thing to do for these countries or whatnot. Okay, and this is exactly the question of a causal inference with observational study. That is, what would happen to United States under different interventions. Okay, and so in a nutshell, viewed from lens of tensor, causal inference, whether it's experimental or observational or a mixture of thereof, is all about doing tensor estimation. They're estimating all the missing values in tensor as well as denoising the observed data under different sparsity pattern of observations. So in a sense, this brings us closer to the problem of tensor estimation, which is reasonably well studied in the world of machine learning. And so now I will keep going back and forth between the tensor estimation and the method as we go forward. All right, so what we have done so far is I've told you a prototypical question in terms of policy evaluation in the context of COVID-19 for causal inference with observational study. We set the question through this lens of tensor estimation. Now let's understand sort of how synthetic intervention tries to solve this problem. Okay, so in a nutshell, the question that we are going after is what sorts of sparsity patterns in tensor can be solved in a statistically and computationally efficient manner. And in this talk, I will discuss synthetic intervention as a method that will try to address this question when the problem can be modeled as a tensor factor model under specific sparsity patterns. Okay, so with that, let's get started. And first, we'll focus on policy evaluation, that is observational study, which is the typical question we discussed. Then we'll go to experimental study. And if time remains, I will talk about some of the theoretical results that enable all of these methods. All right, so in a nutshell, here's what's happening. We are trying to understand what would have happened to United States under, let's say, a severe mobility restriction like this, even though we are observing only United States under low mobility restriction. Now, suppose somebody told me that United States is exactly like this other country that went through severe mobility restriction, then I would say, aha, maybe I can use what happened to that other country that is exactly like United States, see what happened to that under severe mobility restriction because it went through it, and then extrapolate it to what would have happened to the United States under severe mobility restriction. That is, in a nutshell, we want to leverage data from other units. And the question is that how do we learn this relationship? Well, one way to learn this relationship is look at the data that we have before intervention, where all the countries were in the same intervention, and then restrict our attention to only countries that have gone through severe mobility restriction and try to learn somehow a relationship from that. So there's a lot going on here, but in a nutshell, key idea is very simple. That is, try to find similar countries that have gone through an intervention of interest. And if you know the traditional literature and recommendation system, this should remind you of things like collaborative filtering. So that's very much what is in spirit. Of course, methodologically it's different, but hopefully that gives you a way to think about what's coming. Right. So in the method that I'm going to describe, usually we will need that the units of interest, even though they might go through different interventions over time, at least for some amount of time, and this may not be actually time, but for some part, they must experience common intervention so that we can sort of learn the relationship between them. Okay. So of course, this idea is an age-old. As I explained in spirit, it shows up in the classical collaborative filtering or recommendation system. It was beautifully formalized in this work on synthetic controls by Alberto Abadi and co-authors. Alberto is my colleague at MIT from whom I learned these things. And they use this in the context of synthetic control. What synthetic control tries to do is tries to solve exactly the type of question we've been talking about, but in a specific setting. The setting where it's trying to estimate counterfactual in absence of any intervention. So going back to our setting, let's imagine that we want to understand what would happen to the United States if it did nothing, not even low mobility restrictions, no restriction. Okay. And let's assume that there are other countries out there in the world which also did nothing after the day zero. Then what we can do is we can try to learn relationship between outcomes of United States. So again, remember that columns here are time instance, let's say days. Y, which is the target of interest, which is health outcome observations in United States reported daily. The Z, think of them as features. Basically, each column is observation on a given day across different countries, pre-intervention. So as we look at this part, really these are my features and these are my labels, and I'm trying to learn some linear relationship between them. Okay, and this is my, let's say, a linear model. Okay, once I have learned this linear relationship, pre-intervention, I'm going to use the post-intervention data where other countries did nothing, so they remain the same, and then I will simply multiply them by the model learn just the way we do in linear regression and estimate impact. That is, this would be my estimate of what would have happened to United States if there was no intervention. So in a sense, it's extremely simple. It's as simple as it sounds, and as you will see, synthetic intervention is also just this simple with a little bit of change. So this model is what's known as synthetic control, because traditionally this synthetic control or the model is restricted to be the sum of, so non-negative vector, where the sum of the or L1 norm of the vector is 1, that is like a probability distribution. So in a sense, this weight has a nice intuitive explanation, that is the W or model that we have learned is like, if let's say this beta has two coordinates, one is 0.7 and another is 0.3, it says that United States is 70% like country 1 and 30% like country 2. Okay, so it's a nice interpretation that way. Okay. And once you have that, then you can sort of do this extrapolation. Okay. Now, synthetic intervention, which is the natural generalization of it, is not just about absence, but also presence of intervention and multiple interventions. So the scenario that we had was, let's suppose here are different countries pre-intervention or on the day 0, that is 80th death in each of those countries. There was nothing that was done effectively. After that, some countries remain under low mobility restrictions, some moderate and some high. And we want to understand what would have happened to United States under each of these three things and all other countries too. So I want to simultaneously know what happens to all countries under all possible interventions. Okay. Again, so we will do the same thing as we did for synthetic control, but with little change. So let's suppose I want to know what would happen to US here in this slice. Okay, so just as before, I will look at pre-intervention data for US here. Now I'm going to restrict only to the rows that have experienced this blue intervention. And then learn relationship between Y and these rows, or this row and these rows, with by restricting to them. And I'm not going to sort of restrict it to the convex combination, convex or non-negative numbers, and I'll talk about that in a second. But after we learn this relationship, whatever this beta comes out, we'll use that, multiply with this blue outcomes for these units and estimate this. What if I want to estimate the row here in this green slice? Well, I will learn the relationship between this and these rows. That's another beta. So again, this beta would be different from the beta learned here. So beta learned here is relationship between this and these rows. Beta learned here is relationship between this and these rows. But once I do that, then I'm going to use the Z post here to estimate this. This is what we call synthetic intervention, and for each intervention, it's with different donor groups or different countries, so to speak, and hence it changes. Okay. And the way we do this is we don't restrict it. However, in a nutshell, first we denoise this matrix, let's say Z pre and Z post together through a standard matrix estimation procedure like hard singular value thresholding. And after that, we do simply ordinary least squares. This, in a nutshell, is a nice, nice regularized regression, and that works really well. Okay. Now, one thing that sort of you must have noticed by now, as we went from synthetic control to synthetic intervention, is we learned relationship pre-intervention. That is when countries did not have any policies imposed, but then to extrapolate, we use the same model, but when these countries were under an intervention, let's say green intervention. So in a sense, we transferred the model between countries pre-intervention to post-intervention, which are different. It's like, why should a relationship between health outcomes of United States and 3 countries in low mobility restriction should hold true in the same manner between United States and those 3 countries under high mobility restriction? Okay. But in a sense, that's a fundamental driving assumption of this method. So the question is, when does this work and why? Okay, so now I'll present a simple model which I will call a tensor factor model, and that will, it's just a natural generalization of a matrix factor model or factor model. Has been utilized in econometrics, also has nice relationship to exchangeability and all that. So it's a nice generic model and reasonable to believe that this ought to be true. And of course, as we'll find in these case studies, we find it very effective. So let's discuss what this model is. Okay. So what this says is that the matrix of potential outcomes has a low tensor rank. In particular, it has a decomposition that looks like effectively rank R decomposition with U's corresponding to units or countries or rows. V's correspond to time, corresponds to these columns, and W's correspond to different intervention. Putting it other way, at least in a simple setting, let's suppose I want to understand what would be the measurement, true measurement M associated with unit N, day or time T, and intervention 1. Well, it's UN times VT times W1. If I go laterally from here to intervention D, the first two remain the same, but it's W that's changing. Okay. Of course, if I keep myself same W and same U, but go across T, then across rows, then it's U that changes, and across columns, then it's a V that's changing. Right. So each unit, each time, and each intervention has their own factors, and this is simply a tensor of that. Okay. If we focus on one of the slices, let's say this dth slice, it could be written as U VD transpose, where this second part is changing with D, but from the purpose of units, it remains the same. So across all the slices, U's are remaining invariant. And this is precisely the reason, as we'll see in a second, why the model transfer works. Okay. So let's just sort of look at one quick calculation. It's like talk should have one at least calculation. I might have two, but this is a very simple calculation, so hopefully you won't mind it. So since we have rank R, the matrix U is R-dimensional, that means that other than R rows, for most all other rows, I can sort of have a linear relationship like this. Let's assume that its first row is one of these rows, where first row can be written as a linear combination of n minus the remaining minus one rows. Okay. Now, if we have this as a relationship true, then when we look at, let's say, outcomes associated with row 1 at time t under intervention D, that can be written as, in the standards of our model, as this form. Now, replace U with this relationship, we get this, do the change of summation, take the beta out, and then sort of look at the rest. Of course, because of this matrix or tensor form, it's nothing but linear combination of observations in the nth row at time t. So effectively what this says is that in the dth matrix, first row is a linear combination of all other rows with the same weight independent of D. That's why learning the relationship pre-intervention, it holds true under different intervention. And this is exactly what we mean by synthetic intervention works and exists. And in a sense, as a special case, this also argues that synthetic control exists, which is traditionally assumed as an axiom in the synthetic control literature. Okay. One might ask a question, okay, now we understand the model exists, but when can we generalize it? So a simple geometric view of generalization would be that, look, I've got the singular vectors associated with rows pre-intervention, Let me look at the submatrix post-intervention and then look at the singular vectors associated with them. These are two things I do observe in this observation pattern, so I can find them out. And what we must have for this method to work is that span of this must be at least belonging to the span of this, because if this is not true, then method is not likely to work. Of course, this is not sufficient, but this is necessary condition. Now, this necessary condition, we can verify it in a data-driven manner, and that's why we are stating it here. And once we have this, a nice, simple linear algebraic constraint, we can build a hypothesis test and build sort of a simple generalization theory on it. Now, one subtle difference that arises as we sort of focus on this as a condition to do generalization is, on one hand, it avoids distributional assumption. On the other hand, it requires one to think out of the box in the traditional generalization theory. For example, in traditional generalization theory, one would argue that, well, your generalization error is what would be the training error plus some bound that you would obtain based on the model class. Here, because pre-intervention and post-intervention, these are completely different distribution, we might not have that as a luxury, but this kind of condition allows us to sort of argue the generalization without much problem. Okay, and if time will permit, I will talk about this as I talk about some of the theoretical results. Okay, let me sort of, so as I mentioned a second back, this enables us a very clean hypothesis test. In particular, this condition implies that if I take my U post and then project it on the space of the singular vectors obtained from pre-intervention, then I should sort of still retain it. Of course, I don't know this exactly, but I can approximately estimate it. So this gives me a test statistics. And for this test statistics, we can sort of say, we can find out explicitly what this threshold should look like for a given confidence level alpha. Okay, and this helps us that if my test statistics is larger than this T alpha, then I will reject null. Otherwise, I will not reject null. And this serves as a hypothesis test that we use everywhere. And this provides now hypothesis test for synthetic control literature that was missing in the literature. Putting everything together, what we find is under this tensor factor model with right details, and I've not presented you details here, but there are all details out there in the paper that's on arXiv, that the average mean squared error in the generalizations that are counterfactual error scales like 1 over T naught, where T naught is the number of observations that we used to learn the synthetic intervention model. This is the rank of our pre-intervention setup. And rho, which I have not spoken yet, but we allow in our model for fraction of data also missing. So if everything is observed, of course, rho is 1. If data is missing, then the error would scale like 1 over rho to power 4. And there's a sort of additional dependence on the true underlying model parameter we test out. Okay. All right, just to do quick comparison with synthetic control literature, and there's a very rich, very large literature. There's a beautiful survey that was written in 2019 by my colleague Alberto Abadi, so you should definitely look it up. But at the bird's eye view, synthetic control always focuses on just a target. There's one row, one intervention, and talks about only control. And details of generalization error has been missing. The good data-driven test, but quantitative guarantees for them are missing. Through this method, what we found is that, of course, not only we recover what's synthetic control, but we allow for different interventions, simultaneously deal with all units and the control and the treatment. And this is the finite sample guarantees we get with this hypothesis test. Again, this hypothesis test is necessary condition, not sufficient conditions. In that sense, one-sided, but it's better than what was before. Okay. It's worth just closing the loop with what we know in the tensor estimation literature from machine learning. And again, this is a very high level view. So with that, traditionally in the tensor estimation literature, if we think of n by n by n or 3-order tensor, computationally efficient method requires samples scaling like this, and the observations are at random, which allow you to recover entire tensor. Here, what's happening is that we have this block sparsity pattern with appropriate conditions, and that allows you to recover a tensor of similar form with similar amount of data with principal component regression, which is effectively ordinary least squares, and that's at least an upper bound on that complexity. Okay. Now, of course, I want to make sure this is not a horse race because these are different types of patterns, different types of goals. But more importantly, our hope is that now translating causal inference problems from potential outcome framework into this tensor estimation problem, now we can have explicit conversations about computational and statistical trade-offs that were missing, at least in the way we know causal inference. It can allow us to think about different types of experiment design through different sampling, which we can recover through different tensor estimation methods. And more importantly, in my mind, it also gives us a lever to start thinking about individual treatment effect that has been largely missing in causal inference literature, but we could potentially start going towards that. Okay, so there is if one thing that you remember from this talk, if nothing else, is tensor estimation is one lens of causal inference. So maybe solve different types of tensor estimation questions. Okay. So with that as an introduction to the method and high-level explanation of method, but hopefully method was simple enough to explain how to use it, and some theoretical results. Maybe in remaining 6 to 8 minutes, what I would like to do is to explain how this can also help us not just do observational studies, but also do personalized randomized control in a data-efficient manner. So let's imagine that we have n units. Say you've got n different type of patients, and you have d different type of drugs. Okay, and what you want to know is that for each patient type, what is the best drug? Well, if you have patient 1, you would give, or patient type 1, you would give them drug 1, drug 2, drug D, and see their outcomes. And decide, well, patient type 1, drug number 27 is the best. And patient type 2, drug number 3 is the best, and so on. Which means that you would effectively do number of patient types times number of drug many experiments. These can be costly, this can be ethical, and many times it's impossible because you may not have enough patients of a given patient type to do across these many drugs. In the traditional randomized control, where you say, I'm going to ignore patient type. For entire population, I'm going to only decide one effective drug. What we do is that we take patients, and then all of them gets one of the D things, and whichever is the best, so you produce an outcome. And in a sense, this gives you n experiments and one policy for all. Now, what we would like to argue that we can achieve this goal by effectively having a pattern like this. That is, patient type, few patients will get drug 1, few patients will get drug 2, etc., and few patients will get drug D. And also, all patients will get control. And because of this, what's going to happen is that we will achieve this level of personalization with 2 times number of patient groups, rather than experiment scaling with D, which is number of interventions. So it will be constant rather than scaling with interventions. So how can we do that? I would explain that through this beautiful and extremely rich case study from developmental economics by Abhijit Banerjee, Esther Duflo, Matt Jackson, and their colleagues. So I will briefly describe this experiment or this experimental study that was done in collaboration by these group of academics along with Haryana government in India. It's a tour de force case study because it's so really required going and gathering data at individual level over a long period of time in a careful manner. So I will not be doing any justice when I'm just giving sort of 5 minutes of my time describing the study and explaining what outcomes are. But hopefully this gives you some sense of the importance and the depth of it. What they were trying to do is the following. They were trying to decide among 74 different incentive mechanisms, which of the incentive mechanism is best for inducing villagers in India to go and get immunization. Okay. So while this sounds a very simple problem, it's actually a problem and that really needs addressing. And that is primarily because of lack of incentives. So what they did is that they did the study over 13 months. They had 74 different interventions and a control, and they had 2,500 plus villages. Each village got, so for each village, there was a time when there was nothing, that is, they were under control, and then there were measurements for 4 months in terms of immunization. And after that, some villages got a control, some villages got intervention 1, intervention 2, and 74 different interventions. Okay. And the interventions of the combinations of different type of amount of money, different types of SMS reminders, and different types of sort of word of mouth information spreading as well. And the question is that at the end of these experiments, can we decide which intervention is the best? Okay. Now, of course, given the way they had set it up, it was single randomized control. So their suggestion was that let's come up with one policy for all villages. But given the data is perfectly suited for our setup, we asked the question, can we use the data that's already there and use it to extrapolate to say that what would happen to different village under different intervention, and then come up with personalized recommendation for each village separately, because villages are heterogeneous, and so different village will have different effect under different intervention. Okay, so here is a quick summary of these things. What this table is showing is for different interventions across villages, we're trying to understand whether we can sort of verify hypothesis tests that we have. And if we have, we don't reject null. Under that case, what is the sort of the best policy recommendation that we have versus the randomized control? Okay. And randomized control trial would simply aggregate impact across all the villages rather than sort of personalizing it. And in a sense, R square RCT says that how much better compared to just traditional RCT can our method do with respect to the ground truth. Okay. And these are the cases where we focused on the ground truth, so that because we had it. And so this is simply a set of villages for which this was implemented, and hence we can sort of measure the ground truth. What you're seeing is that for most villages, the hypothesis test is not rejected. For some, hypothesis test is rejected, and hence we cannot trust those results. For the ones which we can trust results, what seems is that our R-square is pretty high, which seems to suggest that there is a serious heterogeneity in villages. In particular, RCT is not a good proxy for them. And more generally, if we look at, if we do synthetic intervention-based personalized policy per village, we get a 2.8 times increase in normalized sense over immunization rate, versus one best RCT policy over everything just has 1.3. So this is factor 2x much better than what you were having compared to, let's say, random policy. So definitely there is information out there, and that can be utilized through method like synthetic intervention. So suggest that sort of one should sort of spend time thinking about using such methods for policy recommendations. All right, I'm coming to end of my presentation. It's 3:51. So instead of going through sort of next section where the primary theoretical results driving the method, which is about principal component regression for error in variable regression, I'm going to leave that. Hopefully these slides will be made available online. But just to remind ourselves, what's happening is that when we do learn a model between the target and the units, what we are trying to do is effectively learn a linear regression where covariates or features are noisy. We denoise them, and then so we do ordinary d-square, and this is exactly what's known as principal component regression, which is more than 40 or 50 years old method. And what we surprisingly find is that unlike lasso-based methods which require model information, this is completely model agnostic. And it has, I'm going to skip this for a second. It has best possible rate that's available out there as if it's like a linear regression. Okay, so now what is surprising is that such a simple method, which is core of synthetic intervention, for error and variable regression, it achieves the best possible rate in a model agnostic manner. And it sort of provides us excellent way to generalize counterfactual predictions, even when sort of the distribution changes. All right, so with that, I think I'm going to stop and sort of put this conclusion slide. So as I mentioned, if nothing else, please do sort of take one thing away, that is tensor estimation is an excellent lens for synthetic intervention or causal inference. And synthetic intervention is just one method, but there might be many things that are hidden once we start unraveling this connection. And in this talk, I told you about the method of synthetic intervention, which is statistically meaningful under tensor factor model. Is a nice hypothesis test. We looked at a bunch of experimental case studies, primarily in the policy evaluation. I didn't discuss two other case studies that we have, one in the large e-commerce case study as well as life sciences. And happy to talk, respond offline, and the paper on arXiv also describes that. Some of these things I primarily focused on single metric, where only one measurement, but actually you have multiple measurements rather than one. And that just leads to a higher order tensor, and that naturally generalizes it. There's also, right now we are talking about interventions where we think of intervention 1, 2, or 3, but if interventions have covariates, we could use it to generalize it for when interventions are much, much larger than units. So there are all sorts of natural extensions that one can think about, and that can be carried out in a natural manner. All right, so with that, don't want to overstay my welcome here, and sorry for going over by 4 minutes. Let me pause and see if there are questions.
Okay, let's thank Professor Shah again for the very nice talk. And as for the questions, the first one is regarding how to quantify the intervention in the experimental studies where you have unobserved confounders.
Perfect. So I think so this is a very nice classical causal inference question, right? So at some level, unobserved confounders, right, are nicely captured through tensor factor model. Okay. The tensor factor model says that there is a latent features associated with interventions which drive your observation. Okay? And those factors associated with interventions are not observed, but they are consistent with the tensor factor model. And once they're consistent with tensor factor model, that effect is already accounted for. So just to repeat myself, the tensor factor model, like classical econometrics factor model, takes into account the unobserved confounders through the latent variable that models the factor associated with intervention.
Mm-hmm. I see. Thank you. So basically, if I'm understanding correctly, by imposing the tensor factor model, you incorporate the unobserved latent variable.
Absolutely. And now, of course, one can question whether tensor factor model is a good model or not. But like any other studies, one has to restrict to certain, let's say, certain framework. And this is the framework we are looking at.
Mm-hmm. Thank you. Thank you. And another question is regarding whether we can go one step further by considering multi-stage interventions.
That's a brilliant question. So let me paraphrase your question a little bit. Suppose you have intervention 1, and let's say the United States was in low mobility intervention. Now on day 15, we decided to have high mobility restriction, which effectively we had because we went through a reasonably severe lockdown. And then we come back and we do a low mobility restriction. So we are constantly changing intervention, and hence one has to constantly apply different, let's say, reevaluate the model, so to speak. And of course, like synthetic intervention, it cannot sort of remain true throughout one model. So one has to relearn this. So short answer to the question is that indeed one has to think about a more generalized model to account for how, let's say, intervention now will impact intervention in future, and intervention in future impacts the intervention then and in future. So there's some form of a time series like model with intervention accounted for, like classical control has to come into play. And one way to think about that is think of tensor factor model with time series component being impacted through different intervention, and that has to come to play. And that's sort of one way to think about it. And we've been trying to actively investigate that type of model. At least through empirical studies, we found that type of classical control theoretic inspired model pretty effective in accounting for multiple interventions. But again, sort of, we haven't fully finished the case study to the extent that we feel confident about that. So take this as a answer as with a grain of salt.
Thank you. And maybe the last question. The last question is that in the block sparse tensor model, it seems that you have a confounding effect due to the block sparse structure. I was wondering whether there's a way to remove that confounding effect.
Again, that's a fantastic question. Just to paraphrase your question, when you have block sparsity, what you are trying to argue is that, well, maybe the unit that went through intervention 1 versus intervention 2 has already sort of, in some sense, there is confounding there. Now, putting it another way, that confounder, as you're talking about, would be captured into the unit's latent feature itself or factor, which we are not observing. But as long as your observations are consistent with that unit latent factor, okay, that confounding effect is already taken care of through this latent factor model. So again, there are multiple types of confounding that can happen. One is through interventions, another through the unit itself and relation between them, and either through the latent factor associated with unit or latent factor associated with intervention, or both are subsuming that in this model. Of course, that will mean that potentially those latent factors are much higher dimensional, but at least for the purpose of explanatory power, that is definitely captured in this. So those are fantastic questions, by the way.
Thank you. So I guess I'm running out of all the questions. So thank you again, Professor Shah, for the great talk.
Well, and again, thank you all the organizers for making this kind of seminar series possible. My congratulations to you all for making this off the ground in this times and providing us ways to learn more things. And thank you everyone for hearing me.
Yes, thank you. So also thanks everyone for joining today, and we are looking forward to seeing you guys next week.